Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 12 on the tangent function. You probably were wondering where tangent went to, right? We made it all the way to Lesson 12 in the only trigonometry unit in this entire course without talking about the tangent function, which you saw last year in geometry. So let's jump right into it and start to learn about how the tangent function relates to that of sine and cosine. Here we go. So, the tangent ratio. The two most important trigonometric functions are sine and cosine. Recall from geometry that there was a third trigonometric ratio known as the tangent ratio. In this lesson, we will examine the tangent function. Let's recall how it was defined using right triangle trigonometry. Let's take a look. The right triangle trigonometry definition of tangent. The tangent of A is equal to the length of the side opposite angle A divided by the length of the side adjacent to angle A. All right, so remember back in right triangle trigonometry, we always keyed in on an angle and we learned that the sine was the opposite divided by the hypotenuse, the cosine was the adjacent divided by the hypotenuse, and the tangent was the opposite divided by adjacent. And honestly, in applied problems, you might recall from geometry, the tangent probably came up even more than either the sine or the cosine. So let's jump right into exercise number 1 and sort of review what we could have done with tangent back in geometry. Exercise 1. In each case below, you should be able to immediately give the value of one of either sine theta or cosine theta. Do so, and then find the value of the other, and that of tan theta, with the help of the Pythagorean theorem. All right, great. So just a little right triangle trig, nothing to do with the unit circle. When we look at letter A, right, we've got a right triangle, angle theta is listed, we've got the side adjacent to angle theta, and we've got the hypotenuse. That means that we can immediately say what the value of cosine is. All right? So I can say that cosine theta is equal to the adjacent side divided by the hypotenuse, 4/5. Great. Now, anytime we have a right triangle and we know two of the sides, we can always find the third side using the Pythagorean theorem. Now, many of you can probably just look at this and you already know what that third side is. But say that you don't know what that third side is, maybe I'll call it A, then I could easily say that A squared plus 4 squared is equal to 5 squared, which means A squared plus 16 would be equal to 25. A squared would be equal to 9, and A would be 3. Because this is the famous, 3, 4, 5 Pythagorean triple, all right? So I'll just put a little 3 there and maybe do that so that we can really see it. Now that we've got the side opposite of theta, we can give the values of the two other trigonometric ratios. We can say that sine of theta is equal to opposite divided by hypotenuse, and tangent of theta is equal to opposite divided by adjacent. All right, so we can get all three of them. Let's take a look at letter B, which is considerably messier. So in letter B, we've got theta, we've got the hypotenuse, which is equal to 2, and we've got the side opposite of theta, which is equal to 1. So what I'd like you to do is pause the video now, try to state the one trig ratio that you can, the value of it, use the Pythagorean theorem to find the missing side length, and then try to state the other two in the simplest form possible. Pause the video now and see what you can do. All right, since we've got the opposite side and the hypotenuse, we can immediately say that the sine of theta is equal to 1/2. Now that should actually look kind of familiar to you. You've seen quite a few angles that have a sine value equal to 1/2. But let's not worry about that for the moment. Let's again call that A, and maybe we'll do a little bit of A squared plus 1 squared is equal to 2 squared. So A squared plus 1 is equal to 4. A squared would be equal to 3, and the best that we can do is say that A is equal to the square root of 3. So not nearly as nice as in our last triangle where we had, integers for each of the three sides. Here, our adjacent side is equal to the square root of 3, so we can say that the cosine of theta is equal to the square root of 3 divided by 2. And again, I'm hoping for those of you that have been with me the entire unit, you kind of look at this and you say, wait a second, I think I recall some kind of relationship between root 3 over 2 and 1/2. But let's not be too concerned about that right now. Let's figure out what tan theta is, right? The tangent of theta is going to be the opposite side over the adjacent side. Now, I have no problem with 1 over root 3, neither does the AP exam in calculus, but a lot of math teachers prefer that we not leave a radical in the denominator. So in order to remove it, we do something called rationalizing the denominator, and we're going to do that a little bit on and off today, primarily with the square root of 3, strangely enough. So we just multiply by square root of 3 over square root of 3, and we get that the tangent of theta is root 3 over 3. All right. And again, to me, either 1 over square root of 3 or root 3 over 3 are completely acceptable, but I think this is more likely to show up in terms of a multiple choice answer. So, you always want to kind of refresh your memory on how to rationalize the denominator, and that's it. Okay, now let's kind of move on and start talking about defining the tangent function. Just as we did with sine and cosine, we can also define the tangent in terms of the unit circle, all right? So makes sense, right? Because we want to be able to extend the tangent so that we're not just dealing with the tangent of angles that are acute angles in right triangles. So let's look at exercise 2. Consider the unit circle shown below. Answer the following questions based on this diagram. Letter A. If x comma y represents a point on the circle, how can we define the tangent function in terms of this point? Right? So here we go, right? We've got our angle drawn in standard position. We're calling it theta, okay? X comma y is the point on the unit circle where the terminal ray on the angle intersects the unit circle. So we've got that right triangle drawn in. What can we say that tangent of theta is equal to now, just in terms of the coordinate point x comma y? Pause the video now and see if you can think about what the answer should be. Well, we know that the tangent of theta should be the opposite divided by the adjacent, but that should just be y divided by x. Now, I'm just trying to get that off of there. There we go. Before we even move on to letter B, I want to point something out about this that I think is helpful to think about as we work on tangent throughout the rest of this unit, which is all of 3 more lessons, right? Y divided by x, right, is really rise divided by run. So the tangent of the angle truly is the slope of that ray, right? That's all it is. It's really the slope of that line, right? Because we're starting at the origin, so we're moving x units to the right and y units up. Tangent has this nice equivalent to slope. The tangent of theta is the slope of the terminal ray that passes through the unit circle. But anyway, and so let me actually put that down. The slope of the terminal, and I'll come back to that here and there. It's not the most important thing to understand, but it is kind of cool. Let's now take a look at letter B. Given how we define sine and cosine, how can we define the tangent function in terms of sine and cosine? All right, well, this is really cool. Remember, on the unit circle, the cosine of this angle is equal to x, and the sine of this angle is equal to y. So what is the tangent of theta in terms of sine theta and cosine theta? Pause the video now and see if you can write something down. Well, again, on the unit circle, y is equal to sine theta, x is equal to cosine theta, and so the tangent of theta, which is y divided by x, must be the sine of theta divided by the cosine of theta. And that is now how we will define the tangent of theta in terms of the unit circle. It is simply the y coordinate divided by the x coordinate, or the sine of theta divided by the cosine of theta. All right, now let's start working with the tangent defined using the unit circle. The tangent of special angles. That's right, our special angles are back, and yes, we have to be able to deal with them. So, the definition of tangent in terms of sine and cosine, tan theta equals sine theta divided by cosine theta. So now, let's start to kind of go through that in terms of exercise number 3. Use the unit circle and the definition of tangent in terms of sine and cosine to find the value of each of the following. Do not leave any complex fractions. All right, great. So we're going to be using exclusively radians. I've got the unit circle kind of sitting here so that we can see it. All right, so let's do this. Tangent of pi over 3, right, by definition, is going to be the sine of pi over 3 divided by the cosine of pi over 3. Now, if you simply remember y divided by x on the unit circle, that's also awesome, right? Because then when I go to pi over 3, I see that the y-coordinate is root 3 over 2, the x-coordinate is 1/2, and this is going to get a little bit ugly. Root 3 over 2 divided by 1/2. But now let's go back to dividing two fractions. Let's do stay change or stay keep flip or whatever, right? We're going to take this fraction and we're going to multiply by the reciprocal of this fraction. I always forget how that mnemonic goes, right? This then is equal to 3/2 times 2 over 1. Those two cancel. We get root 3 over 1, or just the square root of 3. So the tangent of pi over 3 is the square root of 3. Now, by the way, of course, your calculator can tell you this as well, but it will tell you this in terms of sort of like messy decimals. So just for a moment, right, just for the time being, if I've got my calculator out, make sure that it's in radian mode. If I go to trig and I go to tangent, and I get rid of my scary little thing going on there, and I go pi divided by 3, right? It tells me that the tangent of pi over 3 is this ugly decimal, 1.7320, etc. Now, what we just saw was that the tangent of pi over 3 should be the square root of 3. So if I type in square root of 3, I see that it is also 1.73, etc. Therefore, verifying at least what we see from our work, that the tangent of pi over 3 is square root of 3. There are some calculators that will tell you just straight up, tangent of pi over 3 is square root of 3. More advanced versions of the TI Inspire will actually do that for you, but those particular types of calculators aren't allowed on certain exams, so you have to be careful about those. All right, going back, let's take a look at tangent of pi over 4. All right, this is one of my favorites. Tangent of pi over 4 is going to be the sine of pi over 4 divided by the cosine of pi over 4. But of course, the wonderful thing about that is that pi over 4, which is at 45 degrees, has a sine and a cosine that are exactly the same. So square root of 2 over 2 divided by square root of 2 over 2. And anytime we divide a number by itself, we get the number 1. Now remember what I said about tangent being the slope of the terminal ray, right? If I actually draw in that line, right, that terminal ray, then that definitely has a slope of 1 over 1, right? For every 1 unit we move to the right, we move 1 unit up, 1, 1, etc. Right? So that definitely has a slope equal to 1. No question about it. Let's keep going. Let's get into one that's a little bit more messy. The tangent of 5 pi over 6. All right, what I'd like you to do is pause the video now and see if you can simplify this one. Couple heads up. It's going to be negative. All right, that's just going to be the way it is. And it's going to be a little bit ugly in terms of radicals. So pause the video now and see if you can figure out what the tangent of 5 pi over 6 is. Okay, well, tangent of 5 pi over 6, by definition, the sine of 5 pi over 6 divided by the cosine of 5 pi over 6. If I go up to my unit circle, trying to keep that in the frame, right, then what we've got at 5 pi over 6, the sine is 1/2, and the cosine is negative square root of 3 over 2. So 1/2 divided by negative square root of 3 over 2. Again, let's use state change flip. So we're going to have 1/2 times negative 2 over the square root of 3. In this case, the 2's cancel. and I'm left with negative 1 over the square root of 3. Now, just like the problem that we started with, I would love to be able to just leave it as negative 1 over the square root of 3, but we're going to rationalize that denominator by multiplying the top and bottom by square root of 3, and we get that the tangent of 5 pi over 6 is negative root 3 over 3. Please note, of course, that we would expect every tangent value in the second quadrant to be negative, because it will always be the y-coordinate, which is positive, divided by the x-coordinate, which is negative, and a positive divided by a negative is always a negative. All right, one last one for you to tackle on your own. Why don't you try to figure out what the tangent of pi is? It's actually going to come out to be a very, very nice number. Okay, well, the tangent of pi is equal to the sine of pi divided by the cosine of pi, right? On the unit circle, pi is at 180 degrees. The sine value is 0. The cosine value is negative 1. So we get 0 divided by negative 1, and we would never want to leave it like that. And we find that the tangent of pi is 0. Now again, remember that whole tangent is the slope of the terminal ray? Well, if I drew this particular ray, right, that's a horizontal ray. A horizontal line has a slope equal to 0. So it makes a lot of sense that the tangent of pi will be 0, as likewise the tangent of 0 will be 0. Right? So again, I encourage you to think about the tangent just a little bit as being the value of the slope of that ray. It also kind of makes sense that if I've got something that's going like this, right, through the origin, either in the second quadrant or the fourth quadrant, that thing's going to be a negative slope, so the tangent will be negative in the second quadrant and also negative in the fourth quadrant. All right, enough of that though. Let's move on. Angles where tangent is undefined. Because the tangent function involves division, right, sine of theta divided by cosine theta, there's a chance that it could be undefined. So let's take a look at that scenario in exercise number 4. Consider the angle theta equals pi over 2, or 90 degrees. Letter A. State the values of sine and cosine at this angle. All right, this should be pretty easy, and if you have to, refer back to the unit circle, but I really do want you to be able to just think about this as, okay, I've got a unit circle, I'm up here at pi over 2, right, 90 degrees, what are my values of sine and cosine? Pause the video now and go ahead and state those. Well, given that this point on the unit circle is 0, 1, we therefore know that the cosine of pi over 2 is equal to 0, and the sine of pi over 2 is equal to 1. Awesome. Now for letter B. Why would the value of tangent of pi over 2 be undefined? All right, well, pause the video now. Try to figure out what the tangent of pi over 2 is using the definition, not using your calculator, although we'll look at that in a moment, and then see if you can think about why the tangent of pi over 2 would have to have an undefined or non-existent value. Okay, so the tangent of pi over 2 would be the sine of pi over 2 divided by the cosine of pi over 2, which would be 1 divided by 0, and we should have it. Division by 0 is undefined. Always and forever. Division by 0 is undefined. Now, just one more time, at least one more time, right? If the tangent is truly the slope of the terminal ray, well, that's the terminal ray. It's a vertical line, and vertical lines have no slopes, or better yet, they have undefined slopes, right? And we saw that in geometry. You may have even talked about it in Algebra 1. But here, again, we see that connection between the slope of the terminal ray and the value of the tangent. Great. All right, let's keep going. Do a little bit more work with tangent here. All right, exercise number 5. At which of the following angles is tangent undefined? Now again, tangent will only be undefined when the cosine, the denominator of tangent, is equal to 0. So take a look at these 4 choices and consider that. Okay, so it will only be undefined, and I really want to be keying in on this, only undefined when cosine theta equals 0, which is the x-coordinate on the unit circle, right? So tangent is only going to be undefined when cosine theta, which is the x-coordinate on the unit circle, is equal to 0. That only happens at the top of the circle, whoops, and at the bottom of the circle, right? Those are the only 2 locations where it could be 0, cosine theta could be 0, and that then leaves us with the choice theta equals 3 pi over 2. And certainly our calculator knows that. In other words, if I take my calculator out and I go into trig and I choose tangent and I do 3 pi divided by 2, it tells me undefined, right? As well, if I put pi over 2, it would also tell me that it was undefined, right? Thinking about slopes again, if I drew in that terminal ray that pointed downward at 270 degrees or 3 pi over 2 radians, we would yet again have a vertical line with an undefined slope. All right, let's take a look at one more problem. Finding trigonometric values. On a final note, it's interesting that if we know either the sine or cosine of an angle and the quadrant of the angle, or better yet, the quadrant that the terminal ray of the angle lies in, we can find the other 2 missing trigonometric values. So let's take a look at that process in exercise number 6. Determine the value of cosine theta and tan theta if sine theta equals 5/13 and the terminal ray of theta lies in the second quadrant. All right, so 2 important pieces of information here. One of which is that sine of theta is 5/13, and the second one is that the terminal ray of theta lies in the second quadrant. Okay, very, very key here. Okay, so how are we going to do this? Well, one thing that we know is something that we haven't seen for a little while, but you played around with this on your homework a few times, is that the cosine of theta squared plus the sine of theta squared is equal to 1. That's known as the Pythagorean identity. It's also simply the equation of the unit circle, right? X squared plus y squared is equal to 1. So this allows us to solve for 2 possible values of cosine theta. Let's do that first. So I'm going to take 5/13 and I'm going to substitute it in for sine theta. So I'm going to have cosine theta squared plus 5/13 squared. Remember, I don't know that theta is 5/13. I know that sine theta is 5/13. That's going to give me cosine theta squared plus 25/169 is equal to 1. Wow. Right? Now I can say cosine of theta squared, I'm being very inconsistent about those parentheses around the theta, I apologize for that, is 1 minus 25/169. And if you need to, you could do that subtraction on your calculator, but that's 144/169. Now I can take the square root of both sides, and I find that the cosine of theta is plus or minus 12/13. Now it's either positive or negative because that's what happens when you solve an equation that's got a squaring in it and you do a square root. But in a bigger issue, right, it's plus or minus because if we think about the unit circle, right, if we know that sine theta is 5/13, what that's telling us, right, is that the y-coordinate is 5/13, and then there are 2 different locations where that's true, one of which is in the first quadrant and one of which is in the second quadrant. Because we are in the second quadrant, cosine must be negative, right? So cosine theta must be equal to negative 12/13 because, because we are in the second quadrant, right? We are in quadrant 2. So it's got to be negative, the cosine. So that's one of the things that we were looking for, right? We were looking for both cosine theta and tangent theta. So we've got cosine theta. It's negative 12/13. Now let's get tan theta, right? And of course we can get tan theta now because we know that it is, let's try that again. We know that it is sine theta divided by cosine theta. All right, we know that sine theta is 5/13. We know that cosine theta is negative 12/13. We could just do then 5/13 times negative 13/12. The 13s cancel, and we find that tangent theta is negative 5/12. And that's it, right? So we had to know the quadrant, because if we didn't know the quadrant, then cosine theta could have either been positive 12/13 or negative 12/13. And then on top of it, tangent could have also had two different values based on the fact that cosine had two different values. But as soon as we know the value of one of either sine or cosine, and we know what quadrant we're in, we can then produce the values of the other one, either sine or cosine, and then using those two, we can find the value of tangent. And that is definitely something that you're expected to be able to do at this level. So make sure to really kind of pay attention to those problems on the homework. All right, so right back in geometry, you learned about the sine, the cosine, and the tangent ratios, and you defined them all in terms of the side lengths of a right triangle relative to the acute angle that you were trying to find the sine, the cosine, and the tangent of. Great. And then we came along in this course and we said, well, we want to break out of the acute angles of a right triangle, so we oriented ourselves on the unit circle, and we found that the sine was going to be the y-coordinate where the terminal ray of the angle passed through the unit circle, and the cosine was going to be the x-coordinate of that terminal ray. But we still had sort of ignored tangent because, quite frankly, it's not as important of a function in terms of mathematical and physical modeling. It's not a wave, and we'll see that in the next lesson when we actually look at the graph of the tangent function. It's periodic, but it's not a wave the way that sine and cosine are. That being said, we can now orient ourselves on the unit circle, and we find that the tangent function can be interpreted in multiple ways. It can be interpreted as the y-coordinate divided by the x-coordinate on the unit circle. It can be interpreted as the sine of the angle divided by the cosine of the angle. It can also be interpreted as the slope of the terminal ray. All of those are correct interpretations, and they're all kind of helpful in different contexts in terms of thinking about the tangent function. All right, well, we're going to work more with the tangent function in the next two lessons. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.